welcome again to another pen physics video. Today I have something special which I got recently, and this is not because it's Pelikan, which is perhaps my most favorite brand, maker of fountain pens, but because this is a limited edition. It's a special edition. It's the M120 green black. It's actually a replica of the original one made in 1955, I think, by Pelikan. Comes in a nice box. And there it is, the M120 green black. And I guess underneath is a nice leather case. So it's a nice box. Let me get rid of the plastic seal. Hard. Okay, so there it is. It's a beautiful resin for the barrel and the cap. All the metallic parts are gold plated, and they kept the same line for the nib, the same form. It's a steel nib, gold plated. Maybe we can see the Pelikan logo, and this is actually a fine nib. And they have done a beautiful engraving here. Other than that, it looks very much like the original retro edition. It's very beautiful, and with the addition of the piston mechanism that Pelikan provides, it's actually quite robust. And for this pen, so I'm going to try it today and work on the continuity equation, which was recently added in the IB syllabus as one of the options. I'm going to use it with this kind of ink, the dark green. So let me open the ink. And ink the new pen. Always put the cap back so no accidents will happen. Having one of these is handy. And we can do some writing with this new pen. So this is the Pelikan black green M120. The writing is very smooth. The ink is a bit wet. The flow is excellent. The nib responds very nicely to pressure. It's not so much flex. Okay, so let's do some physics with it. I was going to go over the continuity equation. In fluid mechanics. So what this is the following. Imagine that you have a flow tube, so fluid flowing in this tube, and on this side you have an element of volume. This is, let's say, 0.1, and this is 0.2. Another element of volume. and fluid flows streamlined, so there is no turbulence. And at this point you have, let's say, the speed is speed 1, u1, and then at this point the speed is different. You have a cross-sectional area A1 and A2, and then this small distance is dx1 and this is dx2. So one may ask, what is the flow rate, the mass per unit time passing through this point 1? We can call this delta M1 delta T. And then at this position, at point 2, you have the flow rate, how much mass of fluid per unit time. And in the IB, we will make some simplified assumptions. One is that there is a steady state flow, meaning that this is a constant. It does not depend on time, and also it is the same in both, in actually all points. So we can say that no mass is accumulated or no mass is lost at any position. So we can say that this delta M, delta T is constant everywhere. And we can also say that, well, we will use that the mass is density times volume. So what is the flow rate at this position? Delta, well, the mass is rho times V times delta T, but this is rho 1, volume 1, and this has to equal the flow rate at position 2, so rho 2 V2 over T. Now the density is not a function of time, so we may assume that this is true, so rho 1, and then the volume is the area times this dx, delta x. But when you divide by time, the area is constant, the delta x, delta t will give you the speed. So this is simply a1, then u1. And this is equal to, again, the density is not dependent on time, and then the volume is the area times delta x2 or dx2 over t, and this is the speed, ut. And this is basically the continuity. Now, one more simplifying assumption is that the flow is incompressible, so these densities are actually the same in all points in the fluid, which may or not be true, but in the IB we will use this, we'll make this assumption. So this is incompressible fluid, and this was the condition for steady state. Flow. So it comes down to this, that the product of the area times the velocity is constant. And basically this means that if the area changes, if the area, for example, becomes smaller, then the speed will become bigger. And this is what is called the continuity equation. Now it makes, it's actually interesting to examine this problem with more mathematically, in a more mathematically rigorous way, with divergence of the density times the velocity, and in cases where the density will change, so there is a net flow in and out of a tube. But I will do this in another video. Thanks for watching.